Hi, welcome to this lesson on calculus optimization problems. Let's have a look at question 3. A cylindrical paint container made from plastic has a circular base and holds 5,000 cubic centimeters of paint. Okay, so in case you didn't know, this is a nice fact to know that 1,000 cubic centimeters is the same as 1 cubic or 1 liter. So 5,000 cubic centimeters is 5 liters. So this is a 5-liter paint container. The container has a specially designed circular top, and it needs twice the plastic needed for the base. So however much plastic this base needs, so the area of this base, the area for the top of it needs double that amount because it has a very special designed circular top. So it's twice as thick, essentially, as the base of it. So the base only needs a single layer of plastic. So we have two questions here. We want to show that the total amount of plastic needed for this paint container is given by this function. A equals 2 pi rh plus 3 pi r squared, where r here is given as the radius of this cylindrical container and h is the perpendicular height. Then we want to find the dimensions of the paint container that minimizes the amount of plastic needed to create this. Okay, so first of all, let's go ahead and show that the total amount of plastic needed for this paint container is given by that. So let's think about the cylinder. If we had to unwrap it, what will it look like? So it'll have this sort of rectangular look when you unwrap it, where this entire piece here is the circumference of the circle, which is 2 pi r, and then given by the height, which is h here. So this is a rectangular piece. However, there's also two circular bases. There's a top one here and a bottom one here. But the top one needs two amounts of this singular copy here of that circular top. And then this one only needs one amount of that circular top. Okay, so let's have a look. The total area then needed for the paint container, I would say there's 3 amounts of this circular base in total. So 3 amounts of the circular base. So what is the area of a circle? That is pi times r squared, the radius squared. Plus this rectangular piece here. But what is this area of this rectangle? It's 2 pi r times the height. Okay, so if I simplify that, that's going to be 3 pi r squared plus 2 pi rh. And that's exactly what we have here. It's just written the other way around, which is fine. Addition is commutative, right? 1 plus 5 is still 5 plus 1. Okay, so that's the area, but notice the area of the plastic needed for this container is given by two variables, the radius and the height. So if we want to find the dimensions of the radius and the height that minimizes the amount of the plastic we need, then we need to get one of the variables in terms of the other, because we only want a function of one variable. So I have to go back to my question and see what information can I use there. Well, they tell us that this paint container can hold 5,000 cubic centimeters of paint. Okay, so here your r is given in centimeters and your height is given in centimeters. So we keep to that centimeters measurement unit. All right, instead of liters. That was just a nice fact to know. All right, so first of all, what is the volume of a cylindrical container? It's the circular base pi r squared times the perpendicular height. But that must equal 5,000 cubic centimeters. So if I just isolate h by itself, because that's easy, it's just by itself, it doesn't have a square like pi r squared, then I would divide both sides by pi r squared. So therefore, I have h now in terms of r. It's 5,000 over pi r squared. So now I can substitute this back into the area formula. So now I have area of just one variable, namely the radius r. It's 3 pi r squared plus 2 times pi times r times 5,000 over pi r squared. So I can simplify that. So I would recommend simplifying it first. So that's 3 pi r squared. Pi will divide into pi. The radius will divide in once. And 2 times 5,000 is 10,000 over r. So that is the area, the total area of all the plastic needed in terms of just one variable, namely the radius. So that's your independent variable. So to minimize this function, what do we need to do? We need to set the first derivative, a of r, equals to 0. Okay, but how do I do that? Well, first of all, this is the trouble part. So I'm going to rewrite this as 10,000 times r to the negative 1 using exponential rules. So doing the derivative laws now, remember pi is a constant real number. So it's going to be 2 times 3 pi, just 6 pi, times r. And then over here, we're going to have minus 1 times 10,000, so minus 10,000 times r to the negative 2 equals 0. So let's simplify this algebraically. We have 6 pi r minus 10,000 over r squared equals 0. I'm now going to multiply both sides by r squared. So I'm going to have 6 pi r cubed minus 10,000 equals 0. Okay, remember the goal is to solve for r here, and that'll give you the dimension for r that'll minimize this amount of plastic needed. So now I have 6 pi r cubed equals 10,000. Bring over the negative 10,000. Then dividing by 6. So let's create some space over here quickly. So let's select some stuff here. And let's remove that. Okay, so far we have pi r cubed equals 10,000 divided by 6. So I divided both sides by 6. Or rather, I can divide both sides by 6 pi rather. Okay. And then to get r, I just take the cube root to get rid of that cube on both sides. So the cube root of 10,000 over 6 pi. So approximately how large is that? So shift cube root 10,000 over 6 times pi. So that's about 8.095. 8.095. I'm just going to leave it to 3 decimal places for now. Okay, if it was 2 decimal places, I would leave it as 8.10 actually. Okay, but that is r. That is the radius that you need that will minimize the amount of plastic you need here. What about the other dimension h? Well, remember we worked out that h can be written over here as 5,000 over pi times r squared. So we know what r is. So what I'm going to do is I'm going to shift store that value into a. So if I recall a, okay, so that's the radius value. So I'm going to say 5,000 all over shift pi times alpha a squared. That's going to give you 24.286. So 3 decimal places. So that's centimeters. Don't forget the measurement units. Those are important. Okay, so let's say to 3 decimal places, the radius has to be 8.095 centimeters and the height needs to be 24.286 centimeters. Okay, so those dimensions will minimize the amount of plastic you need. And to find out how much plastic, if we wanted that information, we know the formula A here is 2 pi RH plus 3 pi R squared. So what we can do is, on our calculator, I can call shift store B for H. So it's going to be 2 pi times alpha A times alpha B. Okay, so that's 2 pi RH plus 3 shift pi. And then A we said was our radius, so A squared. And that gives you 1852.927. So I'll say approximately, because you want to kind of overestimate. You don't want to have more plastic than you need, not less. So I'd say around 1,853 square centimeters worth of plastic. If you have that amount, you can create this cylindrical paint container that needs the least amount of plastic to create it while still holding a volume of 5,000 cubic centimeters for that paint. All right, so that is the interpretation of this question. Again, we need to make sure that we can manipulate formulae that have 2 variables and make it in terms of 1 variable based on the context of the question, and then be able to find the first derivative algebraically, set it equals to 0, and then solve. All right. I'll see you in the next one.